Hello everyone and welcome back. Today I'm going to talk about generalization. What is generalization in machine learning and what does it represent, and why is it a very important concept in machine learning that will never go away? It is at the foundation of what makes machine learning work. So last time we talked about linear regression, where the data looks scattered like this and we can fit some kind of hypothesis through it, a line. And the purpose is to predict yp based on some input xq. And we said that if we assume a linear hypothesis, so we have h theta x is equal to theta transpose x, where thetas are the things that we're trying to fit, then we can construct a cost function based on that. That is the difference between the prediction of that hypothesis and the data that is given to us, and then we can minimize it. And we said that for some functions we can minimize them analytically. For most of them we can only do it numerically. But the purpose is always to find the best theta, the theta hat, so that we can plug it back into the hypothesis and use it to make predictions. So algorithmically, SGD, or stochastic gradient descent, its purpose is to take this equation and then perform it on a computer until you get to the best theta. And then you take that theta hat, you plug it back into the model, and you get yourself a prediction on unseen data. So the question is, how do we do this cycle in the best way possible, in such a way that we're really getting something meaningful that will actually predict the future, not predict something random, maybe based on the measurements were noisy, so we fit the noise and we just predicted noise. We're not predicting anything useful. We want the most probable prediction given the data. And we said that we can come up with hypotheses that are just interpolations, like k-nearest neighbor. We did linear interpolation as an example, polynomial interpolation, etc., etc. But the question always remains, how do you choose the hypothesis? It's not ax plus b anymore. It could be something more complex. So how do you choose the features? And if we assume a linear hypothesis and we have this form, which is theta transpose x, then the question becomes, does h have to be linear in x? Are we just fitting planes? And in most cases, the data doesn't look like it's a plane or a hyperplane in a high-dimensional space. So the answer is no. It doesn't have to be linear in x. If I give you x, you can transform it into a polynomial in that way. And then you still have theta transpose x, or theta dot x. But now this new x is the combination of these input attributes, where we square them, we raise them to the power 3, 4, or we log them, or we add an exponential to it, or a sine, or just anything you can imagine. And in fact, if you put in sines and cosines with the right frequencies here, you get the Fourier transform if you run that optimization. So this is a very powerful way of taking an input and not just working with it, but rather still working with a nonlinear model in the inputs, but it's linear in the features. All we need to do is construct a feature map. So this is phi of x. And this whole field of taking an input, pre-processing it in some way or another, and constructing a feature vector out of it, and then making predictions is called feature engineering. Right, so we have theta transpose phi x in this case. So now we can write our hypothesis in terms of phis, because phis don't have to be x only, but they can be x squared, x cubed, or any feature vector. So one thing we can do, for example, is if we know that the model passes through the origin, then we can drop the bias. If we know that there is no quadratic term, then we can drop the quadratic term. And this is one way to do feature engineering. Sometimes some features are not relevant, so you can get rid of them because they will add noise to the data. And the question of how you choose phi becomes central. How do I choose phi given the data? Now I have a lot of possible models that I can fit given the same input. So one thing you can do is just fit a line, and this would be a feature that is 1x. Now let's make it more complex. It seems too simple. So how about a quadratic line? So the feature is 1x squared, and you have a parabola. And it looks better. It looks like it's capturing a trend better than what's happening here. I mean, this is sort of linear, but could be more complex. Or you can just make it even more complex and say, well, you can have input 1x squared, x cubed, and maybe even as many polynomial terms as you have data points. In that case, you will fit through all the points. So based on what we've learned from designing a cost function, a square cost function, remember the cost function quantifies the distances. The cost function quantifies the distances between the points and the predictions. So if I can fit all the points, then the cost function is 0. And that certainly minimizes theta. So is the solution to just keep making phi bigger and more complex so that it can fit all the points? Is that the best model? And this is a really important question to think about. Before I proceed, pause and think, what's happening here? Now, if you've thought about it, you will realize that this is really what you want, but it's still not clear that just minimizing the cost function will do it. It's actually clear that minimizing the cost function won't do it. So we just want this. That's the right model. And what's happening here is some kind of overfitting. It's overdoing it. This model is too complicated. And what's happening there is the fact that you have something that's too simple. It's not capturing everything that's happening in the data. So we want this. But to get to this is not straightforward. Here you have high variance. If you just remove one data point, the model will look very different. It's not really capturing trend. It might be capturing noise. We want it to be robust to that change. And here we have high bias. It's very biased. It's away from the trend that it's supposed to capture. So since the purpose of machine learning is to be used in situations where I give you new data that you haven't seen before, and I don't want this to vary the model much, so I want something that's less varying. So one way to deal with this is something you need to think about before you proceed. So one way to do this is you just remove some data. This is the green data. From the data set, you assume, you fool yourself like you didn't see it before. You assume you haven't seen it before. You keep it on the side. And now we call this a test set, and now we fit on the remaining points, which we're going to call the training set. So in the case of a parabola, for example, so you have this trend, and maybe you will fit this parabola. And then you add in the other points and see the losses for these points. And let's say you start with a more biased term, so that's simpler. And so you have a line that sort of fits all these points. And what will happen with the test? So here we will have these points, that didn't extrapolate very well. And so in this case, you will have a very large test loss. So we want to choose phi in such a way that we make this test loss the smallest. So how do we do that? All right, so one way to do it is you start with a training set and a test set. You split the data in two, and then you quantify JTrain, right? This is prediction minus true, and then squared. And you do the same thing for the test. So how do you use these two tests, these two functions? Well, the way you use them is you train on the training set. Then you use that training set to make predictions, and then you want to make sure that these predictions are consistent with the test set. If that doesn't work, you go back and you fix phi. Now, what does the complexity, how does the complexity affect the loss? Right? If I make it really simple, obviously that's not what I want. If I make it really complex, that's not what I want. Right? So you can tell that complexity, there is some sweet spot in complexity. So how do you imagine the test loss to be as a function of the complexity? Try to draw it in front of you. Is it like this? Is it like going up? Is it, I don't know. Try to think about that. And what about the training loss? So the training loss, J theta, will be, some value here, and it will either also go up, down, or maybe wiggle around. I don't know how you want to think about the function. So Let's say you have a simple model. What happens there? The simple model doesn't fit the data well, it doesn't fit the test set well, and doesn't fit the training set well. So you have a large loss. If you have a more complex model, then the training data will get better and better, and at some point, as we saw in the polynomial case in the plot before, is that we'll get to 0. So we start high and we go down. How about the test loss? We will start high as well because it's too simple, and it will get better and better. But at some point, the model will become so complex that it's overfitting on the training set and it's not doing well on the test set. So this is supposed to go down and then back up for the test loss. So training goes down, test loss looks like this. So there is an optimal phi for which the test loss is minimized. Now, great, I've seen these curves before. Can't I just do gradient descent and minimize over the test loss? It doesn't work that way. We cannot run gradients over that because we have a different data set. We cannot actually compute gradients of that sort. We don't have a continuous function like in the case of the square loss. So the only way to do it is to do it iteratively. So we start with these hyperparameters. Phi is now one of these hyperparameters, but there are other choices you can make for your model. And the workflow is you split the data into, you visualize it, you don't only the training set, you can't cheat and see the test set, and then you choose your phi. Once you choose your phi, you choose your hyperparameters, and then you run the optimization, the gradient descent algorithm. And once you do that, you evaluate it on the test set. So here we trained on JTrain, we minimized JTrain, and then we tested on JTest, or the test set. If we don't like it, it seems like it's too large, right? We're still not in the minimum. We think we can do better. We change phi. We change phi, we get a new phi, and then we run that cycle again and again until we're satisfied. When we're satisfied, this is the best theta. We've minimized over JTest, and therefore we get now theta hat, the theta hat we're looking for. So this is called hyperparameter optimization when you're changing these hyperparameters. But in any case, you're always starting with a phi. You predict JTest based on the training set, and then this is how you actually make sure it's going to generalize. You cannot use JTrain to evaluate your model. Now, can you see the problem? Pause and think. It makes sense that you train on the training set and then you test on the test set. And then if you like it, then you're close to the minimum. You can just go with that. But here we're running an optimization algorithm, remember. So what's happening when we're going through that cycle multiple times? So pause and think about it. The answer is that we're optimizing over JTest. So we're actually using JTest to optimize, and we've seen the data set. The whole purpose of a test set is that we don't see it, so we know that we're generalizing over things we haven't seen. But here we've seen it. We even got a loss function on how well the model is doing on that test set. So we've indirectly seen it, and then we're using it to optimize for phi. So this whole optimization process is also overfitting. But now we're overfitting on the training, on the test set. So the problem initially was overfitting on the training set. Now we're overfitting on the test set. So what's the solution? Well, the solution, we split the data even more. So what we do is we have a test set, and now we have also a validation set. We will use the validation set in the loop and keep the test set until the end. So we split the data into 3, training set, validation set, and test set, and then we define the loss function for all of them. It's the same, it's just for over different parts of the data set. So now, the workflow looks like this. We split into 3 data sets, we visualize the training set, we choose phi, we choose our hyperparameters, and then we run the optimization. We get the best theta, we get theta hat. Now we plug it into the validation set. We use the validation set in order to make sure that, of course, we're going to overfit over that because we're going to now do a lot of hyperparameter tuning based on it. But once we're done and we're sure we're going to deploy this model, we need to know this is actually working or not, then we use the test set. And we use the test set and that's it. Then now we can go to production, or we can claim that our model does really well, or we can make any kind of useful claim about generalization. We know that we're actually generalizing. Now, what happens if you're not satisfied with JTest? Right? So you've done all this cycle, and of course you've tested, but it's not working. Like, what do? You just throw the project and go home? Just because there are no sets anymore, so you're actually overfitting, so there's no way for you to tell if you're generalizing anymore. Because you're going to do this again and again. You know, one way to do it is you just don't use it that much. But, you know, of course, this is just a partial solution to a fundamental problem. So sometimes the solution is you just go and collect more data, so that you're always sure you're generalizing over something you haven't seen. And sometimes you can split it into more. It depends what the task is. There's a mistake that's done often in models and in a lot of fields where, you know, there's a test set that people have seen before and they keep testing on it and they try to do very well on it and they give it a percentage. Oh, this did 98% accuracy on the test set, but you've seen it before, so is it a real 98%? Now, the question becomes, the whole process of choosing phi is very tedious, and there's, you know, infinitely many possible phis. So is there a way to automate? I want to find phi from X, from the data. Is there a function, is there a learning algorithm that takes me from X and then extracts the features that are needed to make better predictions? And this will become what neural networks do. Now, here are practical tips how to deal with overfitting, underfitting, making things more complex. It's a bit confusing at first. So one thing you can do is, if it's too complex, if you're overfitting, it means your training set is low, your test set is high, then you can just make things a little less complex, right? Remove features. We'll see later you can actually find algorithms that compress these big features into smaller features by changing them, but keeping the relationship between them consistent. We can also do recursive feature elimination, where we start with all the features and we start knocking them off one by one based on which ones affect the output the least. There are different strategies of doing that. Sometimes people will start from, you know, one feature and then add features until they get something that makes sense. Now there are a set of techniques that are called regularization techniques, and those add a term to the cost function. And there's a big class of these. All machine learning algorithms use these to a certain extent, and they're an extremely powerful way of generalizing automatically without having to go always through the loop. And without having to completely change the model. I'll just add something to the loss function, and that sort of fixes the model. What are these regularization techniques mean? What does this equation mean? All right, so let's think first, if this R is a norm of theta, it's the magnitude of theta, then what happens? Well, if it's an L2 regularization, so here I'm showing an example where I got an optimal solution that's a polynomial with very large coefficients if I don't use regularization. Then I use regularization, so I added an L2 norm, which is this norm of theta. This is simply the first element of theta, theta 0 squared plus theta 1 squared plus theta 2 squared, etc. And then you square root that. And what this happens is it forces the magnitudes of theta to be small. So you go from having 200, 1,000 something, 70 to small numbers. And when you get small numbers, you're more likely to generalize because the function will become less wiggly. That's one way to think about it, less wiggliness. The more technical way to think about it is that we're sort of shrinking the hypothesis class a little bit and making it easier to find something that generalizes. Don't worry if you don't get that. But the idea is that smaller coefficients will generalize better, will smoothen the function in order to predict. Now, We can also use another form of regularization, which is the L1 norm. Same thing as the L2 norm, but it's the sum of absolutes. And the L2 norm, the L1 norm actually also makes small values in the coefficients. It sets them to 0. As you see here, there are two values of 0.1, 0.05. So I add an L1 norm and I get zero terms. So this makes the equation as a whole sparse. So it's, in a way, automating the process we're looking for, the recursive feature elimination. It's eliminating features automatically. And that's what L1 does. It approximates a norm called L0 norm, which is simply counting the number of non-zero elements. All right, so these two ways smoothen the function and allow us to generalize better, and everybody uses them not only in linear regression, but really most machine learning algorithms, supervised learning algorithms that I've seen. So what's the difference between L1 and L2? And let's look at it. Why do they have different effects on the solution? So first of all, this is our loss, if you remember. And this is our optimal theta. That's going to be our theta hat here. And as I said, the L2 norm is sum of squares and then square root that. And how do we think about it? Like, what does this loss function look like? Right? So pause the video and try to think about it. So this is a paraboloid, right? And we've explained why it's a paraboloid. But what is this? Is this a paraboloid as well? A parabola? Well, there are squares, so it might be a parabola. So try to think about, the types of functions where, let's say, I set r to constant. That's how I got the ellipses, right? I set the loss function to a constant, and then I have theta squared plus theta squared equals a constant, right? So this is a circle. So now my contour plots are circles, and they're around the minimum, which is 0, right? If I set theta to 0, that's going to be the minimum of this loss function. And these two loss functions, I add them up with some weight lambda for this loss function. And what I'm looking for is the minimum that's a combination of the two. Usually that's going to be sort of at the intersection of the two. So what's happening is the regularization term is pulling the theta to go from theta hat to go from this minimum to this point. So my theta hat would be sort of at the intersection of the two, in between the two. And for an L2 norm, as you can see, both thetas became smaller, and you get an intersection that's non-zero for both. And so what's the effect of the L1 norm? In the case of the L1 norm, in some cases, when the thetas are supposedly small in the L2 case, in the L1 case, what will happen is, if I have sums of absolutes, then this will look like a square, an inverted rotated square, or a diamond. And think about it, it's because if you do the absolute of theta 1 plus the absolute of theta 2, and that is constant, it becomes a line. And so same thing, the same effect, we're going to pull theta here closer to the center, so we're going to make theta hats smaller. But the intersection, if in the square case it will be non-zero, or in the L2 case it will be non-zero, in the L1 case it's actually going to be 0. So you have more likelihood of intersecting this ellipse with the tip of this contour plot. Right, so theta hat will look like this. And this is one justification why L1 will sparsify, L2 will just make things smaller. So that's it for today, and next time I will talk about logistic regression. What happens if the output is binary rather than a continuous value between -infinity and +infinity? So see you next time. Thank you.